t. Okay, so we are now looking at this. Okay, so this is actually a pretty important lesson in the big scheme of calculus, because we're introducing one really huge topic. It's kind of where it starts. Okay, the average rate of change of a quantity over a period of time is the amount of change divided by the time it takes. We talked about that like driving to school. How many miles did you cover? How long did it take? Then we could convert to miles per hour. Okay, so if I want to find the average rate of change of this function, and believe it or not, y'all did this in algebra, algebra 1, f of x equals x cubed minus x. Okay, so that's a cubic function, right? That's a continuous function. But I'm only interested in it on the interval from 1 to 3. Okay, so whatever this graph looks like, some kind of a cubic function, I'm only interested in a little chunk of it from 1 to 3. So I'm just like taking a little piece of that graph. Okay, only interested in that part of it. And I want to find the average rate of change from 1 to 3. Okay, average rate of change is nothing more than slope. Okay, so it's basically saying just pretend that you have this little piece of function, take the beginning point, take the end point, and find the slope between it. And that's your average rate of change. Isn't that what we did with the drive to school? Like we started 0 miles. When we got there, it was 15 miles. And then we divided by the time that it took. So it's beginning and ending, find the slope. Okay, so look at this fancy notation here. Average rate of change is the amount of change. So I'm going to call that delta f of x. What's another name for f of x? Y. So delta y over change in time, delta t. That's what we did for our average speed coming to school. Okay, now, change in time, I don't necessarily know that I'm dealing with time here. I could be, but sometimes in place of time, it's just delta x. Okay, so change in y. What I'm going to do is find the y coordinate at that ending point, the right-hand point. Okay, well, if I wanted to find that y coordinate, I would sub 3 into the function. Okay, so f of 3 means 3 cubed minus 3. That is f of 3. Okay, subtract the beginning y coordinate, f of 1. Subtract, if I said find f of 1, we're going to sub 1 into the function to find the y value that goes with it. Okay, so I just found f of 3 minus f of 1. Okay, then in the bottom, I'm going to subtract the x's. 3 minus 1. So that's change in y over change in x. Equals, all right, so that's 27 minus 3 is 24. Subtract 1 minus 1 is 0. Over 2, that average change would be 12. So 12 is the slope of the segment if I connect those 2 points. Okay, now if that's a little too fancy for you, the other way to do it is to straight up use your slope formula. Find this ordered pair. Okay, well it would be 1 comma sub 1 in. Clearly my picture's wrong because it should be 1 0. Find this ordered pair, sub 3 into your function. We know now that it's 24. And then just use your slope formula. What's your slope formula? y2 minus y1 over x2 minus x1. Slope is y2 minus y1 over x2 minus x1. And that's exactly what we subtracted here. The y coordinate minus the y over the x minus the x. So we're really just using slope formula. 2 points, slope formula. Okay, so here we go. The slope of a line or line segment represents an average rate of change. Specifically, here's your slope formula, equals delta y over delta x. Okay, so there is your slope formula. If you don't remember it, now would be a really good time to memorize that. Okay, A secant to a curve, maybe you remember from geometry, is a line that goes through 2 points on a curve. Okay, so this line right here is a secant. So it's intersecting that parabola twice. Okay, this dotted line is only intersecting this part of the graph at 1 point. Okay, right, it's, we're going to say right here. Make a big dot somewhere in there. Okay, so this line that just brushes up something and touches it once is called a, anybody remember from geometry? Starts with a T? Tangent line, very nice. Okay, so a tangent line just brushes up and touches it once. Secant kind of goes through the graph or the shape or whatever you're discussing. Okay, this point where that tangent line touches the curve is called the point of tangency. Okay, so it's the point where it brushes up against the curve. Everybody good with that?
Is that also where it would intersect with the secant line?
It looks like I drew it kind of so that it should be. We'll say yes. But I could have lots of, like I could have another secant line up here, but then I can have a point of tangency anywhere on that curve. Like I could sort of roll that line around so that it just touches a different point, but stays on the outside of the parabola. Okay, next page. All right, we have a graph. What does this graph represent? Like read the axes. What am I looking at? Number of flies and days. Kind of gross, huh? Flies kind of gross me out. So we're going to use the point 23,150, which is right here, and the point Q, which is at 45,340, which is up here, and we're going to compute the average rate of change and the slope of the secant line PQ. Okay, so we're just going to straight up use our slope formula. Okay, so I'm going to say y2, 340, minus y1, 150, over x2 minus x1. Okay, well, let's crunch some numbers there. And 340 minus 150 is 190. And 45 minus 23 is 22. Let's see what that reduces to. $8.636. Okay, what would my unit be with this slope? What is this number 190 calculating? Number of flies. And what is the number 22 calculating? The number of days. So flies per day. Or you can write out per instead of making it a fraction. Okay, so what this graph is called is a logistic graph. You did say cubic, and it does resemble a cubic curve. Have you heard the term logistic in biology? Maybe? Have you heard about a population reaching capacity? Okay, so this is what this graph shows. Like say we had, we're examining the deer population around here. Okay, so you start out with a few deer. Oh, they start reproducing. The population increases. It increases, but can it keep increasing at that rate? No. Why? Okay, maybe there's not enough food. Maybe this became a problem I noticed not too long ago in the fall. Like maybe their population is so big, then they start spilling out into, you know, our world, and they start getting killed by cars and things like that, right? So maybe they don't have enough room to live, and so then they kind of start encroaching on our space and things happen to them. Anyway, that rate of growth cannot continue exponentially forever. Otherwise, we'd be overrun with deer, or flies in this case. So what it does is it reaches that carrying capacity, which means like the highest sustainable healthy amount. It said that's why it's leveling out up here. So it kind of looks like an S. Kind of resembles a cubic curve in a way, but anything that's like living, a population, is always going to have this type of logistic curve. Okay, so let's answer these questions down here. What does the point 23,150 represent? Okay, on the 23rd day, I'm just going to say day 23, same thing. There are 150 flies. That doesn't have anything to do with the rate that they're changing. It's just on this day, that's how many there are. What does the order pair 45,340 represent? On day 45, we have more. Surprise! There are 340 flies. Okay, and we already did this. I did it above. I got ahead of myself. This is finding the change in the population. So we already did that up there to the right. So we already know that the slope of secant line PQ is 8.636 flies per day. What does that slope represent? Okay, I could phrase it several ways. Would you say, Madison, or was that you? Yeah, the rate of growth, or would you say?
The average increase in flies.
Okay, over the span from?
Day 23 to 45.
Right, okay, so let's kind of combine those two. So the rate of growth, let's say population growth, because it's not the fly size that's growing, right? Rate of population growth from day 23 to day 45. And let's put a word in front of rate. Average. Does it mean that every day between 23 and 45, that's the rate that it's growing? No. In fact, if I look at this graph, I'd say it's growing pretty rapidly here, but pretty slowly here. So that's the average rate of population growth from day 23 to day 45. Okay? Now stop me if you have a question. Okay, so we already mentioned this, but average rate of change is nothing more than your slope of a secant line. You have 2 points. You plug them into your slope formula. Okay? What if we wanted to know the average rate at which the fruit fly population grew on day 23? The slope of the tangent at point P would work, but we cannot find the slope from P to P. Why? So in other words, find point P. Okay, if I want to know how fast the population is growing on that day, I'm going to guess it's pretty high. Not so high up here, but how can I find that? Well, let's just say I'm going to draw a tangent line to this curve at this point, and I'm just going to find the slope of that tangent line. Well, what would I do from P to P? And if I did from P to P, then delta x is going to be 0, and that'll be undefined.
Could you just find it like for another instance?
Okay, that's exactly what we're going to do. So one way of finding an approximate answer to our question about the rate on day 23 is to find the slope or rate of change of a point closer to P. Okay, let's label point A, B, and C. All right, we're going to pick 3 more points. We're going to choose them. All right, let's do let's do A farthest and get closer as we get to C. Let's find some points that we can sort of approximate, and this is totally going to be an approximation. What about if I moved to this point right here? I'm going to call that A. Okay, give me an approximation for A. 35, 310, okay. 35, 310. Okay, let's find a point B that's a little bit closer. Let's do this point right here. I'm going to call that B. What do we want to call that? Like 29, 250? Is that good enough? And then let's pick a point C that's even closer. Ooh, what if I go really close, like right here? Let's call that 25. What do you think? 25, 180. Okay, I'll take that. Okay. All right, so let's split this up because we don't need to do it all 3 times, and then we'll borrow answers. All right, if you're in that far row over there, you find the average rate of change between P and A. If you're in this middle row, you find the average rate of change between P and B. That just means slope formula. And then over here, we are going to find the slope between P and C, and then we'll just share answers. Okay? So use your slope formula and the 2 order pairs that you have. Okay, so the people who found the slope between P and A, what did you get? Lily, what'd you get? Do y'all agree? Okay, we're going to borrow your answer. Flies per day. Between P and B, what did y'all get? 16.6 repeating. Okay. And then we got, between P and C, 15 flies per day. All right. Which one of these would most closely approximate the rate of change on day 23? Probably between P and C. So the 15 flies per day. And why is that? Yeah. Yes. Because C is closest to point P. So the closer we got, ideally, the more accurate our approximation would be. Now, ideally, how close would we want that point to be? Like so close you almost can't tell they're 2 different points, right? Okay, so as we move the points closer together, the slope of the secant line began to approximate the slope of the tangent line. A more sophisticated way of stating this, as the amount of change in time became smaller, the slope of the secant approached the slope of the tangent. Okay, so visually what that means is I had a secant line. Okay, but as I changed this endpoint to become closer and closer to the point P, then I still had a secant line, but that secant line became really, really close to the tangent line. So the slope of that secant began to resemble the slope of the tangent. Okay, so get some fancy stuff here. The limit as time approached 0, we were shrinking that window of time, of the slope of the secant equals the slope of the tangent. So guess how we find out how it's changing right at that moment? We want to find the slope of that tangent. So we want those 2 points to become super, super, super close together, and then find the slope, and then we can say, okay, that's about the slope of the tangent, so that's how it's changing at this particular time, not over an average. Did we do something like that before? Where we inch two things closer and closer together? Remember when we were finding the average speed of the rock, and we wanted to know the instantaneous speed of the rock? It's the same exact concept that we did then. Oh, look at this handsome guy. All right, so this young gent was around in the 1600s, and his name is Pierre de Fermat. He was French. He was a lawyer and a mathematician, and he made many contributions to calculus as well as just mathematics in general. Okay, so he is the one that figured this concept out. He said the rate at which the value of the function y equals f of x is changing with respect to x at any particular value of x equals some number, it is the slope of the tangent to the curve at that point of tangency. Okay, so he said, all right, this is how you do it. You find the slope of a secant through point P on the curve and point Q nearby. Then you find the limit of that secant, if it exists, as Q approaches P along the curve. So you're letting Q get closer and closer and closer, and then you're finding the limit of that secant slope. And then we define the slope of the curve to be this number that we found in the limit, and define the tangent to the curve to be the line through P with this slope. So that process that we used kind of crudely back here, he's the one that said, okay, this is how we figure it out. This is what we need to do. Okay, so let's take a look at this crazy graph here. Do you see a tangent and a secant? Okay, so the tangent is a little bit flatter, isn't it? Okay, I'm going to take this ordered pair, and I'm going to label the x-coordinate A. I'm going to take this point up here, and I'm going to label the x-coordinate B. Okay, I'm going to say this distance that I changed is h. Okay, so instead of calling this B, I could say, okay, I started at A, and then I moved h more. So what is this value? A plus h. Okay, I'm going to change it. A plus h. So I have an ordered pair A, another one A plus h because I moved h units down the x-axis. And then I have corresponding y values with them. Okay, if this function is just labeled f of x, what is this y coordinate? F of a. Whatever I get when I plug a into the function. Okay, well, what is this y coordinate? F of, plug that in. So f of a plus h. Okay, so this ordered pair is a plus h, comma, f of a plus h. This ordered pair is a, comma, f of a. And I'll say that this is point P, and I'll say this is point Q. Okay, so very generic theoretical ordered pairs that we're dealing with here. Okay, but if I want to do what Pierre Fermat says I can do, then I'm going to find the slope between P and Q. Then I'm going to find the limit as these two get closer and closer and closer. Well, if these two get closer, what is H getting close to? 0. And then that's that whole concept of limit. So I'm going to find the slope and then find the limit as H is getting teeny tiny. Okay, so let's set up our slope between these 2 points. Okay, so here's our 2 ordered pairs, and I'm just going to apply the slope formula. So y2 minus y1 over x2 minus x1. Does anything reduce? Yeah, the a minus a, I can get rid of that. So that helps a little bit. Okay, so that represents the slope of this generic line PQ. Okay, well, I want to say what he set up here, that the slope of the tangent, so the slope of the tangent line at P, which is this kind of flatter line right here, if I want to find the slope of that line, I'm going to find the limit, sorry y'all, as h approaches 0 of that slope. And that will be the slope of the tangent line. Yes?
So, is the reason that this works, is it because they intersect the tangent line and the secant line?
Right. So eventually, remember, we're taking this secant and we're moving this second point closer to this one. So think of this point as being fixed, but this one is inching closer, so that this secant line eventually kind of morphs into that tangent line. Does that make sense? Okay. Now I could find the tangent at Q. In that case, I would let P get closer to Q. I don't know what's up with my voice. I even took my allergy medicine today. Okay. Oh, big dark box. Must be super important. Here is the definition of the slope of a curve at a given point. That's exactly what we just set up. Okay, so if I said I want to find the slope of this curve right here at this point, I want to figure out how it's changing right here, this is how we do it. That's our rule. So the tangent line to the curve at P is the line through P with this slope. So we are essentially finding the slope of the tangent line by letting this distance between the secant points get super, super close. Okay? All right, so let's put it into practice. We're going to find the slope of the parabola, y equals x squared, at the point 2, 4. Then we're going to write an equation for the tangent to the parabola at the point. Oof. Okay, we're going to sketch the function. Plain old vanilla parabola. What's it look like? U going through what point? 0, 0. Okay. All right, at some point over here, there's an ordered pair 2, 4. I'm just going to say, there it is. Okay, then also, let's just have color overload here. What I'm finding is the slope of that tangent line. Okay, so I knew my function. I knew the ordered pair. That's going to be my point of tangency. So I sketched a little tangent line, and what I'm going to find is the slope of the parabola at this point, which is the same as the slope of that tangent, which will tell me how that graph is changing at that point. Okay? All right, so here we go. Here's our rule, but our equation is x squared, so we have f of x equals x squared here. Okay, let's just write this down. The slope will be the limit as h approaches 0 of f of a plus h. Okay, what is a? A is this x value. Because look, it says at the point a, comma, f of a. So a is your x coordinate. So when I see f of a plus h, I'm going to make that f of 2 plus h minus f of a, f of 2 over h. Everybody okay with just that? Okay, so take this function, f of x equals x squared. If I said find f of 3, what would you do? Plug in 3. If I said find f of 17, you would plug in 17. What if I said find f of m? plug in m. So when I say find f of 2 plus h, we are going to plug in 2 plus h. Okay, so here we go. Okay, go to the function f and sub in 2 plus h. Okay, so where there was an x, I'm going to have a 2 plus h squared. Minus f of 2. We know what to do with that. We plug in 2. 2 squared over h. Sub it in, sub it in. Because that's what the function rule is, x squared, so whatever I sub in, I have to square it. So if I find f of 2, I say 2 squared. If I find f of 2 plus h, then it's 2 plus h squared. If that function was cubed, then these would be cubes. So it's kind of like whatever your function rule is, that's what you're doing to these things that you're subbing in. Okay? All right, now 2 plus h, true or false, is 4 plus h squared. I'm going to kick you back to Algebra 1 if you tell me that's true. We got to FOIL it out, don't we? Two plus h times 2 plus h minus, and I know that that's 4, over h. Okay, let's get our algebra on here. That's going to be 4 plus 4h plus h squared minus 4 over h. Okay, the 4's cancel. So I have the slope is the limit as h approaches 0 of 4h plus h squared over h. Okay, I still can't just sub in h equals 0 because it's undefined. But at this point, I can reduce everything. Everything up top has a factor of h. I have h on the bottom. So this becomes the limit as h approaches 0 of 4 plus h. And now I can sub in 0. So I can say, well, I wanted the limit of h to become 0. Now I can just say, all right, fine, it's 0. And what's left? 4. Guess what the slope of that line is? 4. Okay, so we use this as a formula to set up our slope of the secant line. Then we work it into the function, whatever our function might be. And then I say, okay, finally just, fine, be happy. Let h equal 0. And then whatever value is left over, that is the slope of the curve, slope of the function at 2, 4. It is also the slope of the tangent line at 2, 4. Now, if I move that point of tangency, I'm going to get a different slope. But at this point, the slope is 4. Okay, so we did the first part. We found the slope of the parabola at that point 2, 4. Next, write an equation for that tangent line. Okay, so here's my tangent line. I now know that it has a slope of 4. How do I write an equation of a line? Y equals mx plus b. Do I know where that's going to cross the y or the y-axis? No. Okay, I'm going to introduce to you, you've probably seen it before. I know my people did in pre-calc. Point slope form. It is going to be our best friend. Point slope form of a line of an equation is this. Y minus y1 equals m times x minus x1. Okay. Plain old x and y are just the variables. x1, y1 is a point, any point that is on the line, and m is the slope. Okay, so I know a point, and I know the slope is 4. So this point slope would become y minus 4 equals, slope was 4, x minus 2. That's the equation of the tangent line. Now, the good news is, I know some of y'all are not going to be happy with this at first. We usually stop there and leave it. And then some of you are going to be like, that's not finished. We need to distribute. We need to solve for y. You can. But it's also fine to stop there. So, tangent line equation. Okay, so if you just really want to keep going, y minus 4 equals 4x minus 8. And then I would add 4 over and get y equals 4x minus 4. So you can either leave it that way or that way. So the beauty of using this form is all you need is the slope in one point. It doesn't matter if the point's on the y-axis or not. Okay?
You can find that.
Well, you'll have a point that you're using because you're going to have to know that point of tangency. So we always use the point of tangency and the slope. Then we can write the equation. We don't have to figure out what the y-intercept is. I mean, once I simplify this now, I do know what it is, but I really don't care. Question? Okay, let's do some more then. How are we doing on time? Okay. All right, example 4. Let f of x equal 1 over x. Do you have a picture in your mind what that looks like? What is it? Hyperbola. Okay. Let's draw a rough sketch here. Okay, so there's our graph 1 over x. We want to find the slope of the curve at x equals a. Just a generic value. Okay, so I'm going to use this again and set it up. But what is a? It's just going to be a. Okay, all right, so let me write this at the top again. M equals the limit as h approaches 0 of f of a plus h minus f of a over h. You can flip back and forth or write that at the top. All right, so slope equals the limit as h approaches 0. Here's my function 1 over x. If I said find f of 3, it'd be 1 over 3. If I said find f of a, it would be 1 over a. If I said find f of a plus h, it would be 1 over a plus h. Minus f of a, 1 over a, over h. Okay with that? So for this part here, you are just plugging these into whatever your function is. How do I subtract those? I have to get common denominators. Okay, what would the common denominator be? A times a plus h. I'm just going to have to use both of those denominators. Okay, so that means that this one is going to be multiplied by a over a, and this one a plus h over a plus h. So I have to multiply top and bottom so that I'm really just multiplying by a form of 1, not changing the value of the fraction. Okay, so I have limit as h approaches 0. When I multiply that, I get a over a times a plus h, I might distribute in a minute, I'll see, minus a plus h over a times a plus h, all over h. And again, I can't just let h be 0 because it'll be undefined. So I've got to keep simplifying until I can sub in 0. Okay, these are like denominators, so I can combine them into one fraction. So this will become the limit as h approaches 0 of a minus h, all over a plus h, all of that is over h. Take a look at that and see if you can follow what I did there. I had to distribute this negative because that fraction was being subtracted. So that's why the h became negative. Keep your common denominator. Okay, we'll look up top. A minus a cancels. That's nice. So now I have the limit as h approaches 0 of negative h over a times a plus h over h over 1. I'm going to change that h to an h over 1. Okay, so do your keep, change, flip if you want. Or do my little shortcut that I like. Negative h times 1 is negative h over h times a plus h. Okay, with keep, change, flip process there.
Wait, how'd you get the negative h on top?
Because back over here, remember I had to distribute that negative. So this was a minus h. The a's canceled, but I still had a negative h left over. Any other questions? Okay, finally, I'm going to get rid of this h here. It's a common factor. I can cancel it. Okay, so what's left? The limit as h approaches 0 of negative 1 over a times a plus h. Can I finally just say find h is 0? Yes, because what if I say, okay, that's 0, then a plus 0 is just a times a is a squared, so I get negative 1 over a squared. Whew. We had to work for that one. Okay, so this is a generic formula that represents the slope to any tangent line on that function. The next question, where does the slope equal negative 1/4? Okay, well this represents our slope. So if I want to know where the slope is negative 1/4, I'm going to set that equal to negative 1/4 and solve for a. Okay, how about we just cross multiply? So I'll get negative 4 equals negative a squared, which means 4 is a squared, which means a is plus or minus 2. A equals 2 or negative 2. Okay, doesn't that make sense that if I go up to this graph, there will be 2 places where the slope is negative 1/4? Like it might be, I'm just sort of guesstimating, like it might be there and there, but there are going to be 2 places where I have that same slope of negative whatever, any number. There are going to be 2 places. All right, so it makes sense that one place is over here at 2 and the other's over here at negative 2. Okay, what happens to the tangent to the curve at the point a, comma 1 over a for different values of a? Okay, so what I want you to look at is, what if I move this point way down here? What does that slope become close to? 0. Because wouldn't that tangent line become really close to horizontal? And the slope of horizontal line is 0. What about if I move the point way over here? It becomes super close to an undefined slope because the line gets more vertical. And then the same happens down here. This gets close to 0 and this one gets close to undefined. Okay, so how can we say that? Let's say as a approaches positive or negative infinity. That means way out on the right, way out on the left, the slope approaches 0. But as a approaches what? 0, as I let these ordered pairs get really close to where x is 0, then the slope approaches what? Undefined. It actually is going to become negative infinity in both of those places because it's just going to get steeper and steeper and steeper. Okay, all right. All of these things are the same. So if we do a problem that asks for any of these things, we're going to have to do exactly what we just did. Find the slope of the function at a point. Find the slope of the tangent at a point. Find the instantaneous rate of change of a function with respect to x at a point. Or, straight up, find that. All of those things mean the same thing. So if we're reading directions and they say any of these, then this is what we go to. Okay? All right. In the 17th century, so 1600s, European scientists and mathematicians wrote their works and ideas in Latin, the one language that all educated Europeans could read and understand. The Latin word normalis was used for perpendicular. When translated into English, the word normal came to mean perpendicular. So when asked to find a normal line, you're actually finding a perpendicular line. So when you see normal, think perpendicular. It has those Latin roots. All right, almost done here. Next to last example. Write an equation for the normal to the curve. That means perpendicular line. Here's our function, and we're interested in x equals 1. Okay, so what does this graph look like? 4 minus x squared. It's going down. It's downward parabola because it's negative x squared. Shifting 4 which way? I think I heard everything but right. I'm going to the right, which is not going to the right. If I write this y equals negative x squared plus 4, what's the 4 do? Up. Up. It would go left if it was in parentheses with the x. Okay, so that's going to move it up. So I have a downward facing parabola up here at 4. Okay, so that's my graph. We're interested in x equals 1. Okay, well when x is 1, what is the y value? Yeah, plug it in. 3. So that means there's an ordered pair 1, 3 on this graph. And that's the point where I'm interested in. Okay, so what I want to do is find the equation for the perpendicular line to the tangent line there. Whoa, okay, here's my tangent. Okay, the whole process that we just looked at will tell me the slope of that tangent line. But I don't want the equation of the tangent, I want the equation of the perpendicular to that. That's the line I want the equation of. Okay, well, that's okay, because what do we know about perpendicular slopes? They're negative reciprocals of each other. So if I can find the tangent slope, then I'll just do the negative reciprocal. I know a point on the line, and then I can do my point slope. Okay? All right, so guess what we get to do? All of this fun stuff right here. Okay, but A this time is 1. Okay, so I want to find the limit. All right, slope of tangent will equal the limit as h approaches 0 of f of 1 plus h minus f of 1 over h. Okay? If we find f of 1, we already did that. We're just going to plug in 1. And I already know what it is. It's 3. But f of 1 plus h, I have to sub in 1 plus h here. So I have the limit as h approaches 0 of 4 minus 1 plus h squared. All of that is f of 1 plus h. Subtract f of 1. We'll plug 1 into the function and we get 3. Question on that? Okay, got the 3 by finding f of 1, which means plug 1 in for x. So 4 minus 1 squared, just the y value. You got it. Any other questions? Okay. Now it's just a bunch of algebra. Okay, so I have 4 minus 1 plus h, 1 plus h, minus 3 over h. Okay, limit as h approaches 0 of 4 minus 1 plus 2h plus h squared minus 3 over h. I'm going to distribute that negative. 4 minus 1 minus 2h minus h squared minus 3 over h. Okay, good news. 4 minus 1 is 3, minus 3 cancels. So what's left is the limit as h approaches 0 of negative 2h minus h squared over h. In every single one of these, you should get to the point where it all simplifies down. If you don't, then something went wrong. Okay, so now I can simplify that so that I no longer have a fraction. Negative 2 minus h. And at this point, now that we don't have that fraction with h, I can say, okay, fine, h is 0. And what do I have left? Negative 2. That is the slope of the tangent. Slope of tangent. So, if the normal is perpendicular, then what is the normal slope? Positive 1 over 2, the negative reciprocal. Okay, so perpendicular slope is positive 1/2. Okay, do I know a point on this line? I sure do. 1, 3. So I'm going to write the normal equation. I'm going to do y minus y1 equals slope x minus x1. And I'm going to leave it. Bless you. Ooh, question. All right, we got one more in us. Yes, that's a long lesson, isn't it? All right, one more. Instantaneous velocity is the instantaneous rate of change of position with respect to time. From lesson 1:1, the function y equals 16t squared gave the distance fallen by the rock. This was the rock's position function. The rock's instantaneous velocity in time t is the instantaneous rate of change of position with respect to time at time t. Okay, so remember instantaneous change? That means this thing. So we're going to redo this problem. And we're going to, okay, in example 1, lesson 1:1, we found that the rock's instantaneous speed at 2 seconds was 64. We're going to find the speed of the rock at 1 second using this new way. Okay, so here's what I want t to equal. Same thing as saying what x is going to equal. And I'm going to use that same process. Here's my function. So if this is x equals 1, when I find f of 1, I'll just plug 1 in. Okay, so I'm going to find the speed to be the limit as h approaches 0 of f of 1 plus h minus f of 1 over h. Okay, so again, if I find f of 1, I just plug 1 in. But if I find f of 1 plus h, then I have to sub 1 plus h in. 16, 1 plus h squared, minus 16 times 1 squared. Can I distribute the 16 and then square? No. Order of operations says I have to take care of the exponent first, then multiply by the 16. Okay, so that's really 1 plus h times 1 plus h is 1 plus 2h plus h squared. Okay, so look for something to subtract out. There's my 16s. The same, see the same pattern happening over and over again with these. Then what I have left should simplify. Okay, and it will. Everything up top has an h in it. So that becomes the limit as h approaches 0 of 32 plus 16h. Now at this point, you see the same patterns happening over and over. If I let h equal 0, doesn't that whole term equal 0? 16 times 0 is also 0. So I get 32. Now go back to our problem. It was in feet and second. So this tells me that at 1 second, that rock is moving 32 feet per second. So not an average rate of change. At this moment in time, if I could freeze time, that's the speed of the rock. Oh, that's a lot, isn't it? Are we okay? Okay, so you have a few homework problems. Do you want the review now, or do you want to wait till tomorrow? Okay. If you want it now, I have it, but it seems like that was a little overwhelming maybe for us. We need to kind of digest this, and then we'll work on the review tomorrow. Okay? All right.